Good morning, my dear kids. In today's class in the chapter capacitors, we are going to discuss the topic force of interaction between the capacitor and the dielectric slab. When a dielectric slab is placed between the capacitor, will there be any interaction between them? Prior to that, yesterday we had a query like if a dielectric slabs are filled up between the plates of capacitor, why only we have to think in that way? There were two methods I shown. One method is right, one method is wrong. Why only that method is correct? And what is the reason why we should think like that? That is what I'm trying to explain with the first one example. Then we'll go for the topic which is related to today's class. Let me start the class. So in physics, I said, no, the numericals are something very important where the whole discussion revolves around the numericals. I'll adjust it. Oh, some problem is there. I will redraw it. No, read the question. I think that the best, the concept which we were trying to learn yesterday, is available in this question. That's what I'm always insisting you what, like the numerical solving is something very important in physics. Through numericals only, things will be very, very, very easy. This is a dielectric slab. This is a. I want everyone to read question and get into the concept. Read question and try to work out. Yesterday we have done all these things. Let's get into the the conducting square plates with length L are arranged parallel to each other at a distance D, very much less than L. This is a capacitor only. This is nothing but a capacitor only here. Here, this one. There's a distance D, there's the square plate of length L. Only in this region, dielectric slab is put up. Then he's asking, find the bound charge present on lower surface of dielectric. Bound charge. Very, 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 I think it's there in SU Varma. Bound charge, find the bound charge. No, is this capacitor connected to any cell? That's the first primary question. No. Then they were given charges. What were the charges given? The charges given are plus Q and minus Q. Tell me what will happen to the potential difference. This is having a dielectric slab. Potential difference between the plates will be some fixed value. Capacitance also fixed value. So now we know the electrostatics, like E is equal to V equal to potential difference equal to E into D. So what do you expect now? The electric field in the air and in the slab. So here is the slabs. This is slab. No. What should be the electric field in the region where the slab is present and also in the region where the air is present? Should be same, no? The electric field. So we will show that use taking the arrow. So the electric field strength in these two regions must be same. Let that be equal to E1 and E2. Now the electric field is same. Then what is the expression for electric field? So now what about the charge distribution? The charge distribution in this region and this region will be different. So, but you are given a charge is a conducting plate. How come conductors should have uniform charge distribution? Here, not possible. You can break up this plate into two parts. There's a one part and there's other part. Here I'll shade it so that. Oh. Okay, you'll get confused. Let it be as it is. No. Here the charge density at this point will be sigma 1. Here sigma 2. The electric field has to be equal. Any reason for that? Because the potential difference will be same. Either you measure potential difference at this particular point between the plates or at this particular point. It has to be same, no? And the separation is same. So therefore, electric field has to be equal in both the regions. This is one primary condition. So then first we'll write E1 equal to E2. Then what is the electric field in the region where the electric slab is present? Charge density by epsilon R by epsilon naught. Where in air it is sigma 2 by epsilon naught. Here the charge density already indicated sigma 1, here minus sigma 1 minus sigma 2. So therefore from this sigma 1 is equal to epsilon R into sigma 2. Keep it here. There's a one primary equation which we'll be using. Then what is the total charge given to plates Q? So what is that Q should be equal to? Sigma 1 into L into X. Because what is the, hope you are able to imagine this what, and the remaining distance, this will be L minus X. This is the plate. You are seeing only a line. It should be some. No. How much of charge present in this region? So this will be sigma 1, here sigma 2. Hope you are able to understand what I mean to say. The total charge on this plate should be equal to Q, and what that should be equal to? This is L. So the total charge on the plate, I'm taking about the upper plate here. The total charge present on this plate is equal to Q. That is equal to sigma 1 into L into X, sigma 2 into L into L minus. I think this particular diagram is going to really help you a lot. Then we will go for what is sigma 1, sigma R into sigma 2 Lx, sigma 2 L square so what is the value of epsilon R? 4, no? Okay, 4 sigma 2 Lx. So this will become 3 sigma 2 Lx. Plate. Okay, this is a plate. No, Vinayak, Nitesh, make observation, 3D diagram. Huh? Okay, finally, there's a one more equation. What we have, sigma 2, 3 sigma. So this will become equal to how much? Equal to, okay, how much you got? 3. This will become 4, no, totally. 4 sigma 2 x equal to L by 3. Substitute that x equal to L by 3. Two sigma 2 L square. Okay, this is the total charge that is present. So what is sigma 2 now? Now sigma 2 we are able to bring, which is equal to Q by 2 L square. Then similarly, now we'll calculate all the things. So sigma 2 value, I got it. So what is sigma 1? Sigma 1 is epsilon r into sigma 2. Epsilon r is 4 Q by 2L square. So this should become 2Q by L square. So what are the charge density? So now how much of charge we'll find out. We are interested the charge present here. So this will become Q1 equal to sigma 1 into Lx. The charge present in this region. What is sigma 1? 2Q L square into Lx. X equal to L by 3. X equal to L by 3. So 2 cube by 3 will come final. How much of charge present in this region? Q1. The total charge given on the conductor plate will get aligned because of dielectric slab. Able to make it out? The thing. Okay, now is asking let's come to the question. Find the bound charge present on lower surface of dielectric slab. What do you mean by this? The dielectric slab is here. I will show slightly little bit because I have to show the distribution of charge. The gap is what you have to neglect. Here, the capacitor is present. So here the charge here, what happened? The total charge Q will not be uniform, will not be distributed uniformly here. It will have one distribution here. It will have one distribution here. Sir, what about in this distribution? It will be uniform. In this, it will be uniform. But the charge distribution here and here will be different. I'm writing sigma 1 and sigma 2. Now we'll focus is asking on the dielectric slab, what is induced charge? First, you should calculate what is the charge present on this plate. It's not Q1. Now we know if a charge is present on a plate where the dielectric slab is there, how to get the induced charge on the slab? That is what he's asking. The charge on the dielectric slab is called as a bound charge. The charge on a plate is called as a free charge. These are the conventional things which are used in the capacitors. I think we'll take one more diagram so that will be very easy for you. So this is the dielectric slab. The thickness, the gap, I'm showing it so that I can indicate all the charges clearly. Yeah. Now, what is the charge present in this region? The charge present in this region is Q1. The charge present in this region is Q2. Then how much of induced charge? Here the induced charge, it will be negative, no? And here it will be positive. And this will be negative. This idea. Now this charge is what is asking, minus QR. How to find out? Yesterday we brought one formula. What is QI is equal to? Q1 into 1 minus 1 by epsilon R. Yesterday we derived it. So what is the charge in the region where it is there? It is Q1. What is the Q1 value? Q1 value, we got it 2Q by 3. So this is 2Q by 3. 1 minus, this is 4, F naught value, I think 4. Q by 2 charge will be present. This is a charge induced on the dielectric slab. Bound charge, various name, bound charge or induced charge on slab. But you see the way he has asked, the language is also a little bit, we have to be, sir, what is that lower surface? On lower surface means the charge will not, will reside here. If the slab is there, no, slightly below the surface will be induced charge, because the reason for that, how the dipoles will be there, will align in this way, no? So lower surface means, again, sir, is he asking this one? Yes, you can put it here. Lower surface, this upper surface, lower surface, but this charge don't show on the top. He's asking this magnitude plus QI. I agree, but you have to show this minus QI and plus QI not on the top, somewhere inside. He's asking this QI. Magnitude is what he's asking here. This upper surface of slab, lower surface of slab. But you have to show charge somewhere just inside, not on the top, because the dipole will be here, no? There's a meaning of that one. But lower surface means here, he mean to say this one. And don't show this charge here. It'll be wrong thing if you show here. Agreed? So he is asking you, okay, I want charge here. What is charge here? I think that's what we have answered, no? Complete description is there. This is there in IDO. You might have not noticed, but this is the concept of the dielectric slab, the total. So that's why I'm suggesting you, like, if you're doing revision, if you just take textbook, see what's happening now. Seniors are there, outgoing seniors are there. You might be knowing many of them. Ask them how you're revising, how you're doing revising. Let's say I'm taking textbook, I'm revising. Textbook will contain all these things. Any of the textbooks, only 10% of information is there. And you are, in spite of teacher telling, notes you have put in dustbin, total over. Then definitely what you'll be in big trouble. No, you're going to land in a big trouble. Your revision will become incomplete because of these things. Because the thing which are most essential are dumped in the notes, because we cover so many things here, so many ideas are there. So you ask how many of them are having notes? Nobody is having notes. Nobody has gathered. This happens every year. You are also going to do same donkey monkey activity. See, textbook is what? Only information, not possible. You can't revise from the textbook. It's only 5% of that one. The teacher notes, what all class notes is there, will gather so many things. So I don't know what will happen to you, that you don't accept this notes, that one. So definitely you are going to enjoy an exam. Okay, now yesterday's question, now can you answer? Yesterday's question, I'll take there. Huh? I think I can save it. Yeah. Capacitors with the dielectrics. I think the headache started from here, no? I said it's a wrong. Yeah, now you can put a very beautiful reason here. Then I said the second method is correct. Now, what will be the charge? You actually are going to connect it to a cell. The charge which starts flowing here, will it be same charge here and here? See, not like separating. You have to give the conceptual. Gayatri, please do understand. Now, just now I explained the concept that you apply it here. That you have to apply it here. It's not like separating. So here the charge which comes here will split a part of charge will flow here. A part of charge will flow here. Got the idea? Sir, how come, sir, same slab? Look at here. Look at this particular thing. So a part of charge, what happened here will be different, here will be different. So therefore charge density here and here will be different. So it will, like if you connect in a circuit, here one current will flow, here one current will flow. So no question of this. Okay, got it, no? There's a primary thing from there, we have to bring it. Okay, we'll go back to our topic. Now, what was our question? Our thing is force on a dielectric slab. Okay, let's do one thing. How there's a plates of capacitor. How the electrostatic field will be? So this is the plates of a capacitor. Now, how the electrostatic field? This I'll call it as a positive charge is present. Here, negative charge is present. How the electrostatic field, how the lines of force will be between the plates of capacitor. Now, the lines of force between the plates from positive charge to negative charge. I'll show a few lines. This will be the lines. I think this everyone knows. Okay, sir, this will be the lines of force. And it will be uniform. And we know that how to calculate that E also. Is it a large plate? For large plate, it will be uniform. No? So because here, again, the edge effect will come. You know this one. And we know that according to electrostatics, the more charge will be deposited in this region than this one. Here it will be uniform. But at the edge, what will happen? It has to be non-uniform distribution. Because of non-uniform distribution, the field here will not be uniform. So it has to be the fringe effect. Due to fringe effect, it will come like this, the field. And the electrostatic field should be such that it should terminate and originate normally, that I'm unable to show clearly in the diagram, that you have to understand. So this will be the fringing effect, what we can call. The field will, some part of field will pop out from the plate. And what about here, non-uniform? Here in this region, it is uniform. Any reason? Because here the charge distribution will be more. If you look at the charge, surface charge density at this point and this point, at this point, it will be more than this particular point because of the edge effect. So why it will, this is called like a fringing effect. Fringing means it will spill out. The field will spill out from the plates of capacitor. So this will be non-uniform. There's a very, very important part before entering into the topic. There's a E bar, you write it. What is E bar? Still, I'll carry on the same way. Here sigma, charge density here minus sigma. And what is sigma equal to? Q by the charge here plus Q minus Q. There's no problem. So like then all the things go wrong. We are doing ourselves, we are doing problem only in this region. Okay, let's take now I'll introduce a dielectric slab between the plates of a capacitor. Anything will happen to that dielectric slab because of some length is what pushed into the plates of capacitor. I'll copy this so that later we can use it. Anything will happen to dielectric slab. So there's a slab having a dielectric constant K. The charge on the plates is Q. Some X length of the slab is going to get into the plates. And we know positive charge is present here. This is a negative charge. Now this charge on the capacitor, what it does, it is going to induce charge. This positive charge will induce. How it will induce? Will it induce only here? No, it's going to induce in this region. And it will induce, this negative plate will induce a charge in this way. Sir, why you are showing the charge, induced charge here? I think you know the electrostatic field, and it will spill out. No, here, not only here, it will spill out. So shall we go for the charge further showing here? And what about the distribution of charge? Will not be uniform, because you know the field will be like this, because the field will come here. So there's nothing called like a here. Of course, sir, like will there be any induced charge in this region? Are you sure, sir? Will there be induced charge? Anybody? Because how the electric field here will be parallel, no? So therefore, there should not be any induced charge in this region. I think in advance, they may test you with these things also. Be careful. I must not show any charge in this region. So why? Because how the electric field will be horizontal, no? But here it's possible. So what about here from why induced charge? It will be like this. The electrostatic, this green color lines of force will induce charge here. Okay, now look at this. This positive charge on a plate will interact with the induced charge on a slab. So because of that, the force on the slab will be in this direction, F dash. Here, F dash. The net resultant force, how it will be in this direction. So the net force on the slab in what direction? It will be vertically down. And now I'm interested to calculate this force. And what is this? This isolated charge capacitor, no? What we are discussing is isolated charged capacitor. Any conditions? I want that force of interaction. Some X length of dielectric slab is there. Let L be this. It's a square plate. It's a square plate. They will have. So then like a two capacitors are there, no? So shall we break up into these two capacitors? This will become one capacitor. This is another cap. Immediately, please do take help of the all small concepts, what you know. Okay, there's an air field, this one, and these two capacitors, how they are. This is X length. The separation between the plates is D. Here, L minus X, D. So what is the total capacitance? This will call C1, C2. They are series or parallel. They are parallel. So the effective capacitance is given by C is equal to C1 plus C2. We'll find out that and we'll see. What was our condition? We have to calculate that force F. So I'll start with this one. What is C1? K epsilon naught L into X. Yeah, L into X by D. Then epsilon naught L into L minus X into D. So this is the expression for capacitance. Okay, further, I think we can simplify this. F naught L square D. One more, F naught L D. Check it once, equation Kx minus this one. Yeah. So this will be the expression for capacitance. Okay, now let's get the expression for energy. What will happen if I insert a slab? Just I'll bring the slab, some X length, let it be there in between the plates. Then I want this force. Anything will happen to charge. Anybody wants to answer? What can happen to charge? Charge will remain same or varies? charge has to remain same. Q will remain constant. Isolated charge capacitor remains constant. Then, okay, as Q is constant, so I'm going to put Q square by 2C. So we know value. What is the capacitance? Just now we have brought it. F naught L square D plus F naught L X by D K minus 1. Now, if I know potential G, I'll differentiate this. I'll get the force. So F equal to minus du by dx. If I differentiate, now look at the force. Will it be a function of X? Will it be independent of X? Definitely X is there in the denominator. So the force acting will be a function of X. F depends on X. So what these plates will do, it will exert attractive force on the slab. It will drag that slab into the plates. You just place the slab, the plates will attract the slab. So because of that, the slab will accelerate into the plates. I may ask you, what is the maximum kinetic energy of the slab? I think you should take help of your kinematics. You know, if differentiate this, you'll get the force, and a variable force is acting, and you go back to kinematics, variable accelerated motion, you can calculate the maximum kinetic energy of the slab. So in isolated charge capacitor, if you bring a slab and place it between the plates of capacitor, the plates will exert an attractive force that will be that will depend on the distance x, the x length of the slab between the plates. That's what I am trying to conclude here. What type of motion the slab will describe? Variable accelerated motion. Okay, there's about the thing. Okay, this I may not be very interested. Okay, let's go for. If a capacitor connected to a cell, then if I introduce slab, what force it will exert? Shall we call this an attractive force or a repulsive force? Attractive force. What type of motion the slab describes? Slab describes variable accelerated motion. They may ask you these things also. Okay, I'll show complete description. Okay, I'll scroll down. I'll go for the next topic. Now the same thing, capacitor. I'm going to connect to a cell. Then I'll introduce a slab. Then we'll see that what will be the force exerted by the capacitor on the slab. I'll remove this, taking a lot of space. And this is directly connected across the cell. This one. Now I'll bring a slab. Some x length of the slab is there between the plates. Now, volume of the slab equal to volume of the capacitor. All these assumptions will make it here. Okay, let this be the. Already the capacitor is charged. It is having a charge plus Q. This is a slab of dielectric constant K, that epsilon r only will call K. And this is the EMF of cell. So, and length of the plates equal to L. It's a square plate. Some X length is there between the plates. For lower one will indicate here. No, you see this. I want that force. So here, what is the situation? Capacitor connected to the cell and a slab is introduced. So we'll write the subheading here, force exerted by capacitor on slab, force exerted by capacitor on slab with capacitor connected to a cell. Earlier it was isolated. Now it's not isolated. Now tell me what quantity of the capacitor will remain constant. The EMF, the potential difference across it will be constant. I think there's a primary condition. Okay, let's get into this one. Again, anything will happen to slab. Anything will happen to the slab. Yes, again, the positive charge on the plates of capacitor will induce charge and some spill out due to fringing effect. The electrostatic field will be external to plates also. So because of that, we will get here induced charge. Will be uniform, non-uniform, will be non-uniform. They may test you with these things. We should not show any field in this region. This is very important because the electrostatic field here will be in this direction. It will be there. So now the force will be the interaction force between the positive plate and this induced charge on this charge, positive charge and negative charge here, negative positive charge. So the attractive force will be somewhere in this direction. Similarly, F dash. The resultant of this is what? The F, which we are supposed to calculate. Now let's get into, I think, the same equation shall we use, because X length of the slab is there between the plates. X length of slab is there. So directly I'll take this expression, which is going to help us a lot. Huh? This is the expression for capacitance. Then total capacitance of the capacitor. This is now tell me, like, because of force acting, the slab will have a mass. Will have a mass, and what is the volume? And here X. This will be length of the slab is equal to L. So I'll write some condition here. Volume of slab is equal to volume of capacitor. I think is okay. The dimensions, the slab will exactly fill up the gap between the plates of capacitor. There's the meaning of this. Length of the slab is also equal to L. Now, what is my question? I want expression for F. The moment the slab is introduced with X length between the plates, the induced charge, the exerted force and net force will act on the slab. Because of that, it starts accelerating. As it starts accelerating, as X increases, anything will happen to capacitance. Will increase, no? Because when it is fully between the plates, how much capacitance? K times. So as it gradually moves, the capacitance is going to change. Okay, let me differentiate this. DC is equal to, this will be 0 plus equal to 0 epsilon naught L D dx K minus 1, or the change in capacitance equal to F naught L K minus 1 . So this is the change in capacitance. Now look at, come for the capacitor. What quantity of capacitor is constant? Potential remains constant. I think this is something I'll put it here. PD across capacitor is constant. This is very, very, very important. PD, potential difference across capacitor, is equal to E. Now, if capacitance increases, because as the slab moves, capacitance will increase, then what should happen? The charge should increase. Tell me, who will going to supply this charge? The cell. So therefore, some charge starts moving from here. So that charge, I'll write dq. And the dq charge from here will move, because charge should be conserved. Now, after this, dq. So shall we calculate the expression for dq? So the dq is given by dq equal to dc into e. The increment in charge. What is that? The increment in charge. So when the slab moves by a distance, small distance dx, how much of additional charge will flow into the capacitor? Dq. That's the meaning of that one. So this will become epsilon naught L k minus 1 dx e by d, or will have this equation. Very important. Now dq charge we have brought it. But what was our question? We wanted to get F, no? What to do all further? Okay, I have certain thing. This force, will it does any work? F into dx, it does work, no? That's the thing. Then the battery does work because the positive charge is leaving the positive terminal, it is doing work. Then is there increment in energy of capacitor? Yes, it is. So somehow I should bring the energy relationship between all this. So how to bring that energy relationship now? I think this is already we have done so many problems on work done all. Can you apply this? The energy aspect I discussed very widely, previous problems, work done, action agent, all. So we have to apply the same similar concept here also. I want you to analyze. Now, what is the basic equation? We can write it. Tell me what all happened. The work done by cell, where do it will go? The cell does positive work. So positive work means it supplies energy. The energy supplied by the cell, where all it will go. A part of that energy will be converted into increase in electrostatic potential across capacitor. The remaining will be converted into kinetic energy of slab. I think totally different thing here. Earlier problems, what we did, the work done by cell, half of it will go in capacitor. Remaining off will be converted as heat in the circuit. But what about here? The work done by cell, a part of it will be taken by capacitor. The remaining will be converted into kinetic energy of slab. So therefore, in capacitor circuits, whenever cell does work, whenever cell supplies energy to circuit, half of the work done by cell must be converted into heat, must be generated as heat in the circuit. Will you justify this statement? Answer is no. Maybe you have to put it, but here what happened, the half of the work done is converted into kinetic energy of slab. All of you, are you getting? Sometimes this one, these are the most beautiful parts of the total, like in LC magnetism. We are dealing with more energy aspect here, almost this entire chapter. So the work done by a cell, previous circuits, what all we did, heat generated. Here there won't be heat generated. So what shall we write here? Work done by cell is equal to increment in potential across capacitor plus increment in kinetic energy of the slab. That's what we have to write expression. So how to get the increment in energy across capacitor? Already we know dq. What quantity across capacitor remains constant? Potential difference. So shall we write now? Almost we have everything in front of you. Work done by a cell is equal to increase in potential energy of capacitor plus increase in kinetic energy. Sir, how you can say kinetic energy increases? See, if you go back to laws of motion, if a force acts on a slab, it will accelerate. Due to acceleration, speed will increase. Due to increase in speed, kinetic energy increases. Okay, fine. Now, work done by a cell dw will increment in intensity of capacitor duc. What is increase in kinetic energy of slab? Who will increase this force? So here we are going to write it as F into dx. Here is what I brought the F. Now work done by cell, what to do? E into dq. Do we know do dq? That's here. Look at here. We have brought it. Sir, how to bring the increment in internal energy of capacitor? What quantity of capacitor is constant? Cell. What is the potential of a cell in terms of potential difference? C E square by 2. So increment in intensity should be equal to capacitance dc E square dc. I'll write it. F into dx. So we want that expression force. Almost, I think now I'm very near. What is dq? Value will substitute here. This will be E into books. They are given very complicated way. They wanted expression, not the concept. That's what I'm bringing with through the energy equation. DC value already, I think, on the top, no? F naught L K minus 1 dx by d. This I don't know. The F is unknown thing. Let me just this F is what unknown. I don't know that. Okay, I'm not bothered about that. So shall we cancel dx? The primary, the first condition. I'll cancel dx. Then after cancelling this, so this will become F naught L E square K minus 1 2d. Okay, this is d. The same quantity, no? Only denominator, this will become 2d plus f. So what is this final equation? The final equation will end up is very important. You have to remember this. Very important. So many numericals are there. Some around 20 numericals are there related to mechanics. Not 1, 2. The moment you get force, we know what we do in any chapter. we'll go back to mechanics and we'll explore some numerical. This is what happens here. So what is this F? Force exerted by capacitor on slab. Is it attractive? Yes, attractive in nature. Is it conservative? Yes, conservative. Is it a constant? Look at all the values. Yes, it's a constant. Okay, see the complete description. I think primary thing is this is the which you have to, the whole thing revolves around this, writing this equation. And energy aspect is very important. Means like, sir, is it independent of x? This one. Compare the previous one. For isolated charge capacitor, if you bring a slab, the force was a function of distance. Here it's independent of x equal to L by 3, L by 4, L by 2. The force will be a constant. And it's attractive force. What this capacitor will do, will suck it, will pull that slab into the between the plates. What about the heat generated? Very clearly. Work done, half of the work done by the cell will be there in capacitor, remaining will be converted into kinetic energy of slab. So heat generated in the process will be 0. So no heat is generated. So somewhere we have to write it very clearly here. The entire process, no heat will be generated. I'll write it here. Not in capacitor, again related to, okay, I'll write it here. No place, we'll write it here. No heat is generated in circuit. This is, I think, very, important condition. So now in an in a capacitor circuit, a cell, when it supplies energy to capacitor circuit, it must be generated, need not, maybe you have to put it. That's what I am trying to conclude here. Anybody having doubt, you can clarify it. The derivation is, maybe they ask in board exam, but in advanced exam, nobody will ask you. But we have so many concepts. Now, let me move this slab with a constant speed v. Is it possible for it to move with a constant speed v? No. Some extra agent can do, no. Then what is the expression for current to the circuit? Can we find out? If I move this slab with a constant speed v, what is the expression for current to the circuit? From where I should bring this equation? I will take help of this. Okay, now we are going to take all the related numericals here. Some external agent will come into picture and he will apply a force equal to that so that the speed of the slab will be constant. I want expression for current. Without external agent, not possible. The slab will accelerate. So for that, let external agent apply some force, and the slab is moving with a constant speed v. I am asking question. Let the slab move with a constant speed v between plates of a capacitor. Find current through the cell. How to get that? I have enough theory covered. Okay, this was the increment in charge, no? Okay, see, already we have discussed. See, look at that one. Okay, this I am going to bring it here. No. So we know that there's the expression for charge. And what is dx? Sir, can you show dx? Where is the dx? The dx should be here, no? There's a dx. This was the dx here. Dx by dt is what v? Dx by dt is what will become v. Dq by dt is what? The current. I'll differentiate this. So many things are there which will be just covered here only. Now this will become expression for current. F naught it is. So look at this expression for the graph. So many problems are there. All are related to the graph will be straight line. You have these questions in books here. Where how to show current? Current, will it change direction? Because it all depends upon velocity here. Now, if you're moving the slab like this, okay, it'll come this one. Once it fully between the plates, okay. Then afterwards, it will start moving out. No, as it starts moving out, the charge will decrease. So the current what happen as the plate moves from left to right, and anything will happen to charge. First, the amount of charge will increase, becomes when the slab is fully between the, I have here, no, I'll show it. No. Oh, it's not moving. Only slab I should, yeah. Now, as the slab moves, the charge on capacitor will increase. Now charge on capacitor is maximum. So then again it starts coming out of between plates. No, I'm moving it. Then charge on capacitor decrease. Then our current will flow in opposite. Hope you are able to. Okay, there's an expression for current here. Now have few more problems related to this. Let's go for that. We discuss few more better problems. It's coming in every page. Oh, this is coming up. Let me take the same diagram. Will be lengthy. I'll draw a fresh one. Now, what is the next question? I'm going to release the slab. I want the complete motion of the slab between the plates. The complete. I'll show only small diagram because I have to give so many situations will be there here. And the slab is brought between the plates. Some x length of the slab is introduced. The volume of slab equal to volume of capacitor. Having mass m, dielectric constant is k. This is EMF E. Separation is D. What is our question? Find the time period of oscillations of the slab. When x length of slab is placed between the plates of capacitor, where there's a square plates of side length L. So what is your question? You have to find out the time period of oscillations of the slab. Sir, will it oscillate? That's what happens here. So I'll give the question, then we'll go for it. Huh? Find the time period of oscillations of slab between plates of capacitor. So the volume of slab is equal to volume of the capacitor. Or I'll put it here, slab fully fills the volume of capacitor. What is the length of the slab L? What is the side length of the plate? C is equal to L. There's the meaning here. Now he's asking to get the time period. I'll give too much time. You have to think. You have to fight with it. Will it be SHM? So these are the questions we are asking ourselves again. Okay, it is released from rest. The slab is released from rest in this position. Then immediately the plates of capacitor will exert a force F. And we know that force F is a constant. And what is that F is equal to? You have to remember F naught L E square K minus 1 by 2D. Please do make memorization, very important, because you have plenty of application problems. You can't derive this in exam. You have to start the numerical. Nobody will ask you derivation of this. So what they'll ask you, like, based on this application. So I have brought one. So in exams, if you know this force, you can manage. Otherwise, what happens? You have to derive, then come to the numerical. So every chapter comes with certain data, the standard data that has to be memorized. There's no other way. You have to. That's what the type of examinations you're writing. So I don't want to memorize. Okay, you are going to lose certain rank. What type of motion the slab will describe? Uniform accelerated motion or uniform retarding motion. It is released from rest, so it will start accelerating. Then in the next position, I have here paste copy. I'll do it. I'll put all the set of diagrams. In the next position, the slab will come to this position. It will have maximum kinetic energy, am I right? And there won't be any force. Because it will accelerate, no? And it was at t equals 0, we have started here. And this will be t equal to t by 4. Sir, how that will see this? The next one. In the next position, what is the state of slab? Now the slab starts decelerating, no? Yeah, it'll be like this. Yeah, sufficient length is there. So it will start decelerating. How the force will act? Now the force will act in opposite direction. There'll be retardation. K1 you call kinetic energy. K is a kinetic energy of K is a slab dielectric constant. Here K max, K1 are kinetic energy. It will undergo retardation. Then finally it will come to rest. Instantaneous rest, better you call. My job is very easy. Paste copy. Okay, yeah. This is so. Next part will be where do it will come to rest? What length of slab will be there between the plates? Anybody wants to answer? Yeah. I want from answer from anybody. What length will be there? So this will become some intermediate time. This I'll put it t by 2. What length of the slab will be there between the plates? Means same x length. Okay, agree this. Instantaneous rest. Then again this force will act, will pull it back. Again we'll get back the situation. But here how the kinetic energy of the slab will be? The maximum kinetic energy, because the force was acting, no? So here it will be K max. This will become T equal to 3T by 4. After this, finally, it will return back to this original position. I think the whole situation I'm showing at one page only. Do make notice here. No. Finally, it will come back to like this. Is it oscillatory motion or is it SHM? That's what primary we have to ask ourselves a question. Okay, there's a maximum kinetic energy. Then instantaneous rest. Okay, this will become one time period. Then again, so here, so I had to show one more position where it will be like this, it'll undergo retardation, then it will be, I think I'll show that. So it will be this position, it will come, no? When it comes this position, it will undergo. Oh. And there are some around 16 different types of questions are there. Try to work out them. So this will be the some kinetic energy K2. Here the force will be in this direction. Finally, it will undergo retardation and will come to this position. This will T equal to 0 altogether. T equal to capital T will magnitude. This is some intermediate time. No, so many questions are here. Will they be generated? First primary question. Then what about the current? Will it oscillate here also? Current direction also will change, or will it remain fixed here? So the first will start from here. The moment I release the slab between the plates, some x length of slab between the plates, so it will start accelerating. Capacitance will increase. Potential difference constant. Capacity increases. Charge should increase. So these are the logical thinking. Please do bring across capacitor. If E constant, C increases, Q should increase. So from where that additional charge will come? From the cell. Okay, tell me like now, as it starts accelerating, so how the charge will flow in this direction? There'll be flow of current here. So if in fact you have to show it here, there's a current and the charge will flow here. Then afterwards, it has come fully between the plates of capacitor. Here it has come fully between the plates of capacitor. Now the maximum kinetic energy is there. Now, because of maximum kinetic inertial motion, it starts moving towards left. Then as it starts moving towards left, capacitance decreases here. Then charge should decrease. So how the charge now, the same current has to flow here. It will come to instantaneous rest. Slab will come to instantaneous rest. Then again as it starts moving, then again the charge how it will flow in this direction. So now you can look at this. here again what's happening to it. I show intermediate, one more diagram is needed, no? Here coming here. I'll bring one more diagram. Still many students are asking, sir. Oh, I'm really got stuck. I'll adjust the diagram, no problem. Slightly, we have to move the slab. Intermediate diagram, no? I think diagram. Yeah, this will be more justified before reaching. No, clearly you see it. And now this will be some kinetic energy. It will be there. So how the current? The current, in fact, will flow here. If you let there be. So I'm starting some initial current is flowing. Okay, therefore I'm avoiding it. Okay, this will be the current. This will be the charge. This will not be T by 4, time less than T by 4. Here it will have some kinetic energy. Hope everyone is able to understand things. So when it moves, when the slab moves from extreme to mean position, the current will flow from, the charge will flow from the cell to the capacitor. When it's moving again from the mean to left extreme, the charge will flow in opposite cells. So in this way, what's happening there? What conditions are arising? There'll be exchange of energy between the cell and capacitor. There's exchange of energy and no heat generated. This is the ideal we are discussing. Practically, the conducting wires will have a resistance. So there are so many complications are there. There'll be friction between the plates and capacitor. We are discussing ideal world, paper world. What was our question? We wanted to, we are not here artists, not to draw diagram. We were interested to get the time period, how to bring time period. How to bring the time period. What time, if I can calculate this T by 4, okay, no? Afterwards, 4 times of that time period. So can we calculate this time? Time taken to move from, like from in the T by 4, can we calculate this one? So what was the, how much of distance the slab will move to come fully between the plates? Look at this first and third diagram. X length of slab was here. Look at only this edge. How much of distance it will move to fully between the plates? L minus X. And what is acceleration? Constant, because constant force will act. No? In all the cases, you just show F is acting. Here, what about force, sir? Sir, can you say anything about force? No force will act here because the fringing effect will be somewhere in this way. It is not fully between the plates. Now here, force F will not act. Now, because of kinetic energy, it will start moving out of the plates of capacitor. Then capacitor decrease. The charge will flow in this way here. Here, what about how to show the charges? I think here. Okay, this is again, it should be in this direction. Some good conceptual questions will ask. That's why I'm interested. I'm showing all the diagrams, charge flow, everything. Now let's get into our calculation part. L minus X equal to A T by 4 whole square of A T by 4 whole square. So X is a given thing. So X can be anything in length. So do we know acceleration? So what is acceleration? You can write it as F by M. Directly, I'll bring this expression. The next step, we'll write it here. L minus X equal to, already this 1 by 2 I had to adjust, no? In place of A, it will become MD T square by 16. Okay, now solve for T to get the required answer. Hope everyone, I'm trying to put everything in one diagram. When the kinetic energy of slab will be maximum, when at mean position. So you have to call this as a mean position. This again, mean position. So I want that maximum kinetic energy. Can we calculate that maximum kinetic energy? Yes, you can calculate. You know acceleration. Then V square minus U square equal to 2A's formula you apply it. You get that maximum kinetic energy. Let me solve for that T. So the total T will be is equal to 2 16 4 ja 64 L minus X MD by F naught L A. E square minus K1. The time period depends on applied EMF. Time period depends on applied EMF. The answer is no. S. Time period depends upon the X length of slab between the plates. Yes, it is. Because if you make X equal to L by 3, you'll get one time period. If you put X equal to L by 4, you'll get one time period. Try to see this. I think based on this equation, we have to analyze here. There's one very famous, this numerical is there. Possibility of asking as it is in advanced exam. Okay, after this, we'll go for the next one. Anybody having doubt, you can ask. So many conceptual things are there. What about the current, all other things? What about the current here? Constant or variable current? Current flowing the circuit, current I is constant or variable? Will be variable, no? If the if the speed of the slab constant, current will be constant. I'll move to the next application. Yeah. Laws of motion idea. There's a block M1. Then I'm going to connect this to a slab, and this is rough. It's not looking good. Have like this. Now there's a rough surface. This is having mass M2, and this I'm going to connect it to a cell. This is D. Separation is L by 4 length is between the plates. Square plate it is A equal to L square, will write it. So there's a rough. Now the system is in equilibrium. So I want expression for quotient of friction mu. Fine. The system is in find quotient of friction mu. So slowly we are bringing that force into our mechanics here. You need not to bother anything here. You are just bringing that force into mechanics here. Okay, what are the various forces that will come into picture? Normal contact N1, M1G, the friction here, the tension T. The tension T will act here. Then the weight of the slab. There's a slab, no? Any electrostatic force will be exerted by the plates of capacitor S, that is F. Now it's in equilibrium. So it's in equilibrium means, so we will write F minus T equal to 0. F equal to mu M1G minus T equal to 0. Then for the equilibrium of slab, T minus M2G minus F equal to 0. T is equal to, in fact, mu M1G. This is M2G. What is F? Epsilon naught L E square K minus 1 by 2D. Whether it is L by 4 or L by 3, what will be that? So expression for mu will be M2G plus whole divided by M1G, or this will become M2 by M1 K minus 1 to M2G D. M1G D. This is the expression for mu. So now, sir, like along with weight and tension, this force will act as you treated this just like any other force. You get wide varieties of problems. This is what you should try to work out some best numericals which are available related to only this force. That force will be constant. Hope everyone will try to work out some numericals related to this. Like this, you work out few problems which are related to force of interaction between the dielectric slab, this one, between the plates and dielectric slab, and it's a conservative force. This F is a conservative force. You can apply a conservation of mechanical energy also related to these numericals. Okay, I'll bring it one more, which you like it very much. Okay, there's a string. Okay, there's a slab. There are the three loops are set up in this one. Let mu be the mass per, or lambda be the mass per unit length of this. Let L be the length of the rope, and mu be the mass per unit length. The slab, some L/3 length of the slab is there between the plates. L is the length of the slab, and it's a square plate. Separation between the plates is D. Now, what should be the applied EMF? So that three loops will be set up in this rope here. So here a standing wave is set up. Find the applied EMF so that the wire will resonate in the third harmonic. One end of the rope, one of the wire is connected slab, other end to the rigid support. So what can be this? This should be a node, no? String resonates in third harmonic. Find applied EMF E. This is what happens in most of our physics problems. The moment you learn, you will start applying to the other ideas there. Who will provide from where the tension will come? This particular force. So what is this F? F should be equal to T. Epsilon naught L E square K minus 1 2D. This F only will provide the required difference. So if it resonates in the third harmonic, if it resonates in third harmonic, so what is the formula for that? 3V by 2L. 2L. So this V is what? T by mu. And in fact, F equal to T. This tension is what F. So this will be F naught L E square K minus 1 2D mu. Solve for E, you'll get the required answer. F is the frequency will be given, third resonant frequency. Now you can apply some variable force also. You may impart some velocity for this. You may impart some kinetic energy. You can do whatever you want with this one. I just shown some related to different things. So please do work out this one. So don't get scared the moment you see that one. The moment you see dielectric slab placed between the plates of capacitor, you can bring this concept. A constant force will act here. That force will be related to, that force will become a part of a system. Okay, now we'll take the, so let's have a circuit. Okay, this is having capacitance C naught, C naught. This applied EMF E. An external agent will fill up the plate with a dielectric constant of K. What will happen to all the quantities in the circuit? We have to go for all the quantities. So what external agent will do is going to push a dielectric slab into the plates here. So all the quantities, what will happen to charge, energy, all other quantities. Capacitance was how much? C naught and C naught. When you introduce that, it'll become Kc naught. An external agent will fill the above capacitor with dielectric medium. That only I'm calling slab here. Here you call slab. Find the find the increment in charge, find the work done by a cell. We'll compare things, we'll just learn things, what will happen, what all changes will happen here. So initially we'll calculate the charges. What are the charges that are present? We'll remove this. Initially, what are the charges that are present? Initially, be like a Q naught, we'll take it. Q naught minus Q naught plus Q naught minus Q naught. So what is the charge of system? Q naught should be equal to C naught by 2 into E, because effective capacitance will be in series. Then series effective capacitance will become C naught by 2. So this is a charge in each capacitor. So what is the initial energy in capacitor will be equal to half of the EMF will come. I'll write it in another way, or Q naught square by 2 C naught. 2 C naught. So this will become Q naught square by C naught. What is Q naught? Q naught is C naught E naught by 2. C naught E square by 4. This will be the energy, initial energy in the circuit. What was the initial charge of system? It was Q naught. Finally, after it is fully filled up by the, so the slab, I brought it here. Then capacitance of capacitor will become Kc naught. Or any changes in the charge? Yes, some changes in the charge will be there. So we'll take it that as Q. The capacitance of other capacitor will not change, but the charge in other capacitor has to change. First, we'll calculate the total capacitance. It'll be easy for us. The total capacitance of system will be C is equal to Kc naught by K plus 1. Kc naught into C naught, Kc naught plus C naught. So this will be the capacitance. So then what is the final charge? Final charge will be C into E. So this will be K C naught E by K plus 1. This will be the charge in each capacitor. The final energy in capacitor, final energy should be equal to Q square by 2K C naught, Q square by 2 C naught. Q square, I think Q square 2 C naught. First, we'll bring outside. Okay, this one. This will become 1 by K plus 1. Q square value, K C naught E by K plus 1 whole square 2 C naught. This will be 1 plus K by K. 1 K get cancelled. So K, 1 C naught also get cancelled. C naught E square by 2 1 plus K. So this is the final energy. Look at the final energy, increases or decreases. It all depends on K. No, K should be greater than 1, no doubt. The K must be greater than 1. The K must be greater than 1. So put K equal to 3 by 2, check it. Is it UF greater than UI? Put K equal to 2. If you put K equal to 2, C naught E square by 3, C naught E square by 4, the energy got increased, no? K equal to 1.2 like this. But altogether, I should take help of this equation, then I should conclude energy increases or decreases. This will be the capacitance will increase or decrease capacitance. Earlier, what is the capacitance? C naught by 2. Now 2 C naught by 3 will increase, no? Capacitance of system. So like this, they'll ask you in matchings, it will come. If I fill up this, then what will happen to the energy in the circuit, capacitance, charge, final energy. Now, if UF got increased here, who will supply this? The battery. So the battery does positive work or negative work. You have to compare all these things. For that, what you have to do? Just you have to take the initial and final data. With slab not filled, slab after filled. If Q greater than small, if Q greater than Q naught means, what does it mean? The battery did positive work. Because the charge, you just look at the charge of this plate. The charge of this plate increase means the battery should push that additional charge. So positive charge leaves, so the battery does positive work. I think we need all the data without, I think what students are doing is like, they are thinking it's a conceptual, you go wrong there. Initial, final. So you have so many best questions available in textbook now. So initial diagram, not all the things. Final diagram, find out one. Then you compare, then you conclude the options. There's a method. So students, what they think it's a conceptual, close eyes, imagine. No, you'll go wrong. We'll discuss the next situations. If there is a cell, an external agent will pull out the slab from the plates of capacitor. Then we have to discuss what are the conditions. So this will be K, E. This is with capacitance, it is 2 farad. 4 farad will write it. This is 2 farad. With dielectric constant, it is 4 farad. After removing it, it will become 2 farad. I'm going to pull out this slab. This EMF, let me take 10 volt. So external agent will pull out the slab. I'm asking all the things. What about heat generated? All queries like earlier we did. Can you remember yesterday we did know like some external agent pulling the slab or increasing the separation between the plates. Yeah, let me pull in. Let me pull out. Let's get into the concept. So external agent and external agent pulls out the slab from capacitor, from above capacitor, right? From one of the, from capacitor Then find heat generated in circuit. We are again coming back to same idea of heat generated. Before pulling out, we need data. Am I right? After slab brought out, then the data. We'll compare both, then we can analyze. Otherwise, not possible to say anything about the conditions in the circuit. The one which is pulled out, I'll keep it here. Okay, the slab is brought. Who is going to bring that slab? X agent. Then how much capacitance will become? With slab, capacitance was 4 farad. Now after removing that, it will become 2 farad, no? C1 dash, you write it better, justified. Let's get into the calculation part. So earlier there was a charge, say Q. This charge will call capital Q. Comparisons will be easier. We have to calculate that charge. Okay, you can apply anything. So better let me stick on to the loop equation so that I'll not go wrong. Minus Q by C1, Q by C2. E is 10, Q we don't know. This is 4, this is 2. 10 equal to, this will be 1 by 4 plus 1, 3 by 4, 3 Q by 4. 40 by 3 coulomb. I think we'll bring any sum. Yeah, let it be. So there's the initial charge. Okay, final charge will calculate. Final charge will be E minus Q by C1 dash, Q by C2 equals 0. This is 10. Both are having same capacitance, 2. This is 2. 40 by 3. What is 40 by 3? Greater than 10. Q 10 coulomb. So I think a small, some idea we have now. Look at this plate, this particular, any one plate you look at. The charge on this plate increased or decreased. Earlier it was 40 by 3. 13.33 coulomb. Now it is 10 coulomb. So some charge left from here and the positive charge entered positive terminal. So we are able to now predict the work done by the cell. Okay, fine. So what was our query like? Heat generated in circuit. So what to do for that? Because here some extra agent also is there in the picture. How to take care about him? Say extra agent will spend energy first of all. As it starts pulling out, the plates of capacitor will exert force towards left. So he has to overcome that force. So his mechanical energy got decreased. So that energy, where do it will go? He will supply, he will give energy to the system, or he will draw energy from the system. Now, some of the I want from students all this because these are very beautiful ideas. The students' replies are matters a lot. Anybody wants to reply? Yourself only. You are going and there. What you are doing? You are just pulling out the slab. You lose energy. Where do your energy will go? Who will take this energy? Agent gives energy to system. Yeah, that's what. X agent will give that energy to the system. And what is the system here? The overall, like will it give energy to the cell? No, altogether the system here. And how to bring that work done X agent? I think we had earlier discussion very clearly. Work done X agent should be equal to what? Mod of delta U. So whether it's increasing or decreasing, let it be mod of delta U. So again, we'll enter into our old method. The first method, what we brought it, the initial energy plus work done by cell, work done by X agent equal to final energy plus heat generated. We'll solve for H. So first we have to calculate that initial energy. UI equal to Q square by 2C1, Q square by 2C2. Q is 40 by 3. I think C1, C2, we can simplify. 1 by 2 plus 1 by 4, 3 by 4. Instead of squaring this one, then Q square will become 40 by 3 whole square by 2 into 3 by 4. 1 3 get cancels. Here 4 10 400 by 6, 200 by 3. I'm not sure whether I'm correct. You have to verify it. No, final energy will be equal to, again similarly here, Q square by 2 C1 dash. It's a test of patience, because we know concept. Until the data is there, we can't conclude. Q is how much? 10. Okay, this again will be 1 by 2. It will become only just only Q square by 2. So this will become 10 square by 2, 50 joules. Look at anybody says UF is less than UI, no? The potential circuit got decreased. Exchange agent also did work. Where do all gone? Work done by cell heat generated. Is it heat generated? Is there? Yes, we don't know, but we have to calculate it. So I'll proceed here now. This one, UI. I think there's a. I'll indicate by red color. This will be UI. Work done by cell. Work done by exchange agent equal to UF plus heat generated. So I'm telling this one, the electrodynamics by IEDO. Don't go and read again, because already explained. Say there's a major problem with the student. When we say some book, no, then again students will think if you read that book, you can solve any problem. To solve any problem, again, you have to put effort. So don't be in a perception that there is some book. If you read that, you'll get a knowledge. Just in the one of the paragraph, he has mentioned very systematically. In all capacitive systems, if an exchange agent comes and modifies the capacitive system, and if an energizing agent is also an energizing electrical agent is also present, you mean to say cell, then use this particular thing. It's a golden statement here. See, there's a beauty of that books here. So many students will say, sir, no problems, nothing, only story is there. In one of the paragraphs we have just mentioned, just like in a capacitive system, if an exchange agent modifies a capacitive system, and also there's a energizing system is there. Energizing means cell, that one. It can be anything. Here I brought a cell. There can be in any way I can bring the energy, no? You just put energizing cell. So then use this particular formula so that energy will be conserved. Finish over. I think we have some around 60, more than 100 numericals are there, just revolves around that statement. Okay, now we'll substitute all these things. We'll 200 by work done by cell. We don't know that, what to do. So I look at this particular plate. Let me take only one plate rather than this one. Any one plate is enough. The plate which is connected to positive terminal of a cell. I am bothered about only this plate. Look at this plate. What was the initial charge? The initial charge was Q, 40 by 3. Final charge is 10. So some charge left. Then it has become capital Q. So that the charge left is, let me show it here only. Now delta Q into E. Positive charge entered a cell, so therefore I'll put negative. So what you calculate delta Q? Charge left, no? Charge left should be negative. How to calculate delta Q? Again, we will take the thing that one. Initial charge was Q. Charge left delta Q, or it is like this, no? And it has become finally Q. So 40 by 3.
10 by 3, sir.
How much delta Q?
10 by 3, sir.
10 by 3 coulomb. Okay, this will be 10 by 3 coulomb. Now work done by X-ray agent. What to do? Again, we don't know work by X-ray agent. Should be mod of delta U. Will it be positive or negative, sir? What will be that? I think first we'll work out few these things, then I'll go for substitution. We'll calculate these things also. UF is 50. That is 200 by 3. Uh, 150 minus 50 by 3. So take it 50 by 3. Now we'll bring all the things here. Sir, it should be negative. You took mod, so better you substitute negative sign. How to justify? So will you give priority for mass or really some physics is there which has to be taken care? See, to pull this slab, when I'm pulling this slab out, the force will act towards left, no? Then there'll be capacitor will exert force. I should overcome that force, so I should spend my energy. This what here. Equal to final. Finally is how much it is? UF of 50 plus heat.
The heat is 0, sir.
It is 0. Yeah. Delta Q into E. 10 by 3. 10. So no heat is generated in circuit. See, some 100, 200 years back, this was maybe like they proposed long back. You see so much of visionary, the Western science. How to get electrical energy, because this is something, this electrical energy is something very useful for us, no? And what is available for us? Mechanical energy. So can we convert our mechanical energy into electrical energy? This is a system. So now we are at a stage where we are able to convert this mechanical into electrical energy. This was the ideas. Some 100, 150 years back, they have brought all these things and they made students to learn so that future generation can design equipments which can convert mechanical energy into electrical energy. 150 years back, they have thought, just imagine like how much of visionary they have. Many will say, sir, why you appreciate so much? You see that all these are not numericals. The scientists or the students or the teachers who are there, no, the authors who are there, no, they wanted to impart the knowledge so that will be useful for society. They brought that as numericals. If I make numerical, no, it becomes stupid numerical, no doubt. So what all we have numericals till date, it was all 99.99%. All the numericals are having some meaning. Some numericals may not be practically possible, but coming generation, after 500,000 years, we may work out. So this is the power of all this numericals here, especially physics. No, it's about the numericals are not just like some mere question answer. Everything what happened will be implemented practically, if not today, tomorrow. Now we have electrical equipment. You type in Google, no, you have equipment, but little bit they're costlier. Maybe technology improves, they'll become cheap. Then in my home, what will happen? I can generate electric power. I need not to depend on government of India. This is what they're planning future. No, please do work out almost, I think, slabs, everything. Tomorrow, one more set will go for it. Still more conceptual questions on the dielectric slab is what I have to discuss. And there's, I think you check the advanced paper, there's some sort of priority as given in capacitors with the dielectric slabs. He has given some priority. So better to work out some best numericals so that will be in a safer side. I'll wind up the class. Thank you, all of you. Post office box. I'll explain on Friday. Very simple. Half an hour it is. Meter bridge only it is. Or I'll post the video. Better you watch it. I'll post the video, better you watch it.
Thank you, sir.
Okay, thank you, all of you. Try to revise all, think on especially the dielectric slab. Many good application, mixed concepts questions are there that you have to work out based on the capacitor with dielectric slab. Okay, thank you, all of you. Take care. Bye. See you.